Okay, next we will discuss the classical theory of normal Zeeman effect. What is a normal Zeeman effect? A normal Zeeman effect is when a spectral line, a single line, is passed through a strong magnetic field, and if this is observed in a direction which is parallel to the magnetic field, then this single spectral line is split into two component lines. If this spectral line, single spectral line has a frequency nu naught, then this line has a frequency nu naught plus d nu, and this line has a frequency nu naught minus d nu. Like the frequency of these two spectral lines are different from the frequency of this original line. This original line is absent here. This is unpolarized and this is circularly polarized. If we pass through this line through nickel prism, then this remain unpolarized, and these two lines they polarize circularly. This is one kind of normal Zeeman effect. And the other one is if a spectral line, a single spectral line pass through a strong magnetic field, then this spectral line is split into three component line. If we observe this modified light in a direction which is perpendicular to the magnetic field, if this is the frequency nu naught of this single spectral line, when B is 0, here we have B is equal to 0. Here we have B which is not 0. So here we have B is equal to 0. Here we have B which is not equal to 0. Then this spectral line split into three components. The central line has a frequency nu naught, and these two lines has a frequency nu naught plus d nu. This is greater frequency as compared to this one, and this line is a frequency nu naught minus d nu, which is a frequency smaller than this. Now this single line, this unchanged line, when magnetic field is 0, it is unpolarized. If we pass through a nickel prism, then it remain unpolarized. While these three lines, they are plain polarized if we pass through a nickel prism. So this is what we call it normal Zeeman effect. Now we will explain it by using the classical theory. Now classical theory was given by Lorentz. Classical theory was given by Lorentz. Now we will use Lorentz theory to explain the normal Zeeman effect. Suppose we have an electron which is moving in this circular orbit. It's circular, it can be parabolic, yes, parabolic, but we consider a circular type orbit. And suppose that electron is moving in clockwise direction, then the velocity of this electron, the linear velocity, is tangent to the circle at every point. This is the velocity of electron, linear velocity. Now this electron, I consider it its charge is E and its mass is m. Now this electron is moving in the circular orbit, so the centripetal force required for the electron motion is given by the centripetal force Fc, which is given by mv square over r. But we know that v is equal to r omega. So Fc, the centripetal force, which is equal to m r square omega square over r. So r cancel this with this square. So we have the centripetal force, which is mr omega square. This is equation number 1. And the direction of this centripetal force is always directed toward the center of the orbit, Fc. Similarly, if the same electron moving clockwise direction, anti-clockwise direction, suppose the electron is moving in anti-clockwise direction, then the velocity is tangent to the circle at every point, and the direction of velocity is now changed to this one. So again here we have the centripetal force, its direction is inward. Now Here I will plot these two figure again because they are not look perfect. These circles are not look like a perfect circle. So I will plot a circular shape orbit. So we have two cases. Either the motion is clockwise or anti-clockwise. So I'll consider both the cases, okay? So this is clockwise motion. The velocity is always tangent to the circle and the centripetal force is always directed toward the center. This is centripetal force. Here we have anti-clockwise motion of electron. So the velocity is tangent to the circle at every point, the linear velocity, sorry. And the centripetal force is also directed toward the center here. This Fc is the centripetal force. Now, suppose we are applying an external magnetic field which is perpendicular to the plane of this circle. Like this is the circle and I am applying the magnetic field like this. It is perpendicular to this surface. Like it is straight, like it is upward to this plane of this patch. This is the direction of centripetal force. External magnetic field, like the external magnetic field is along B, along Z axis, and this circle is in X and Y axis. So the magnetic field will be perpendicular to this plane of this circle. Now, when an external magnetic field is applied perpendicular to the plane of the orbit, then additional force start acting on the electron. When B is applied in a direction which is perpendicular to the plane of the orbit. Then an additional force acting on the electron, which is according to the formula, this additional force is magnetic force, which is equal to Q charge times V cross B. But here we see that this is the velocity and this is the magnetic field. So both are perpendicular to each other. So it means that the angle between velocity V and magnetic field is 0. I can write it here since this equation can be written as F B is equal to Q VB sine theta. The magnitude. I will find the direction later. Now the magnitude of this force is this one, and we know that angle between V and B is 90. So this magnetic force on electron is QVB. It is QVB, but for electron, Q is replaced by its electronic charge. So we have this force Fp, which is equal to EVB. This is equation number 2. Now, what will be the direction of this force? If I consider here, velocity is this one and the magnetic field is this one. This is the magnetic field. So if I find out the direction by using the right hand rule V cross B, then in the case of clockwise motion, then in the case of clockwise motion, the direction of FB will be inward toward the center. This is the direction of magnetic field. While in the case of anti-clockwise motion, the direction of magnetic force will be away from the center. This is FB. So here the force is, the magnetic force is downward, here the force is away from this center. You can find it by using the right hand rule. So this is the direction of magnetic field. Now in this case, the net force on the electron, which was in the absence of magnetic field, was Fc. Now the net force is the centripetal force plus magnetic force. Here the net force is Fc plus Fb on the electron. And here, in the absence of magnetic field, the net force was centripetal force. But once magnetic field is applied, then the net force is now Fc minus Fb. So here the net force increases and here the net force decreases. So in either cases, the angular velocity of electron changes because we have a different force now. Once we applied a magnetic field, we have a different force here. So I can say that due to this additional force, angular velocity of electron changes. We got this idea from these two because we have an extra force now. Here the net force increases, here the net force decreases. So in either cases, the angular velocity will change. Now let d omega is the change, or be the change in angular velocity. Omega. Like initial angular velocity was omega. Now this is the change in this angular velocity due to applied magnetic field. Now we applied the magnetic field, but the electron is still moving in this circular orbit. Here the angular velocity will increases, here the angular velocity will decreases. But electron is still moving in the circular orbit. So in equilibrium, the equation of motion is like when there was no external magnetic field, the equation of motion was this one. But here we have the external magnetic field we applied, and the external magnetic field is either this one. The net magnetic field is either this one Fc plus Fb, or it's either this one Fc minus Fb. So the net force will be Fc plus minus Fb, which increase just the angular velocity. So we have this part which is m r. Now the angular velocity changes from omega to omega plus d omega. So this is the equation of motion. Like in case of clockwise motion, we have Fc plus Fb, which is equal to mr omega plus d omega whole square. While in case of anti-clockwise motion, we have Fc minus Fb, which is equal to mr omega plus d omega. This is, let's say, equation number 3. Now here the positive and negative sign comes from the fact that in case of clockwise motion, both centripetal force and magnetic force are toward the center. So the resultant force is Fc plus Fb. While in case of anti-clockwise motion, the centripetal force and magnetic force are opposite in direction. Centripetal force is toward the center and magnetic force is away from the center. So the net force is Fc minus Fb. So this is the idea behind this plus and minus sign. Now using equation 1 and 2. Here we have equation 1, which is for the centripetal force, and here we have equation 1, 2, which is for the magnetic force. If I put these two equations in equation 3, we have m r omega square for centripetal force, plus minus for magnetic force we have E VB is equal to, we have this side m r omega plus d omega whole square. I can write it as m r omega square plus minus EVB, which is equal to m r omega plus d omega whole square. This is the final equation of motion, and I call it equation number 4. So I will do rest of the calculation in the next video. Thank you.